What if you could feed an AI a 1,000-page legal contract, or an entire software code base, and have it understand the whole thing instantly, without your computing costs exploding into the stratosphere? Well, a company called Subquadratic just made a claim that could shake up the entire AI industry. They say they have built a model that can reason over massive amounts of text, without paying the brutal computational tax that has limited AI models for years. To understand why this is such a big deal, we need to look at the single biggest bottleneck in modern AI. When you give a language model more text to process, the cost does not grow in a straight line. It grows much, much faster than that. And it all comes down to a mechanism called attention. Transformers understand language by comparing every single word, or token, against every other token. So, when your input doubles in length, the number of comparisons does not just double. It quadruples. If you scale that up from 10,000 tokens to 1 million, the attention compute does not go up 100 times. It scales up roughly 10,000 times. That is a massive computational wall. This is exactly why the entire AI industry has spent years building complex workarounds. We are talking about retrieval systems, chunking pipelines, vector databases, RAG frameworks, and agent orchestration layers. All of this heavy infrastructure exists because models cannot cheaply hold an entire document in their head and reason over all of it at once. But here is the thing, that scaffolding is not free. Every time a retrieval system pulls a chunk of text, it is making a blind bet about what information actually matters. And honestly, it gets that bet wrong a lot. Think about how we actually work with information. If you give an AI a full code base, it usually does not read all of it. It searches pieces. If you give it a legal contract, it retrieves chunks. If you throw financial filings at it, it pulls fragments and tries to stitch together the bigger picture. But that is not how those tasks should work, right? In a real legal contract, one critical term might be defined on page 2, modified on page 12, limited on page 46, and then completely changed in an appendix. If you only look at fragments, you miss the entire context. A code base has functions written in one file, but used across 40 others, tested somewhere completely different, and shaped by architectural decisions buried in a README file that nobody updated. Research means comparing dozens of papers that use similar words but make conflicting claims. In all of these cases, the hard part is not finding one relevant sentence. The hard part is understanding how all the pieces connect across the whole document. Subquadratic calls this whole artifact reasoning, and they claim their new technology finally makes it practical. The core of what they have built is called SSA, or Subquadratic Sparse Attention. The basic idea is that instead of comparing every single token against every other token, the model dynamically learns which relationships actually matter, and only computes those. And wait, this is not based on some fixed pattern or where the word is located in the text. It is based entirely on the meaning of the content itself. That distinction matters a lot more than it sounds. Earlier sparse attention methods were efficient, sure, but they were way too rigid. They followed fixed patterns, like always looking at the last 1,000 tokens, or always covering certain local windows. If the important information fell outside that fixed pattern, the model missed it completely. Other modern approaches, like Mamba, RetNet, or RWKV, try to get around the scaling problem by compressing the past context into a small, fixed-size memory. That works reasonably well for basic summaries, but when the model needs to recall one specific detail from millions of tokens ago, that compression can lose it entirely. Hybrid models try to mix efficient layers with normal dense attention, which helps, but the expensive part never fully disappears. Subquadratic is making a much stronger claim than any of those. They say SSA is linear all the way through, not just the attention step, but the selection step, too. And that second part is critical, because it is a trap that other approaches constantly fall into. DeepSeek's sparse attention system is a great example here. It uses a dynamic indexer to decide which parts of the context to attend to before the attention actually runs. That is clever, but the indexer itself still has a quadratic cost. According to Subquadratic's technical report, once you hit 52,000 tokens, that indexer actually becomes more expensive than the sparse attention it is guiding. By the time you reach 1 million tokens, it costs roughly 16 times more than the actual attention. At 12 million tokens, it is about 190 times more expensive. The lesson here is simple. If your solution to expensive attention is an expensive attention selector, you have not solved the problem. You have just moved it somewhere else. Subquadratic says SSA avoids this entirely because both the selection and the attention scale linearly. To prove it, they just released the model card for SubQ 1.1 small. It is the smallest model in their current lineup, and they are rolling it out to partners now, with massive 12 million token models planned for later this year. Let's look at the benchmarks, starting with the classic needle in a haystack test. This is where you hide a specific fact inside a massive block of text and ask the model to retrieve it. SubQ 1.1 small scored a perfect 100% at 1 million tokens. It scored another 100% at 2 million. At 6 million, it hit 98%. And at 12 million, it still maintained 98% accuracy. That 12 million number is the one that stands out. The model was primarily trained at 1 million tokens, with some extra training up to 2 million. It was never specifically trained for a 12 million token context, yet it still achieved 98% accuracy there. And at that extreme length, it was only attending to 0.13% of all possible token pairs. That is the source of their claim of a 1,000-fold reduction in compute. They also tested it on NVIDIA's Ruler benchmark. Now, Ruler is much more demanding than a basic needle in a haystack test. It covers 13 different tasks, including multi-key retrieval, common word extraction, and variable tracing. It is designed to verify that a model can actually use information distributed across a long context, not just retrieve one obvious answer. At 128,000 tokens, SubQ 1.1 small scored over 99%. But the raw efficiency numbers are what really stand out. At 1 million tokens, one pass through normal dense attention takes about 252 petaflops. SSA? Just 3.9. That is a 64 times reduction on a single attention layer. At 256,000 tokens, it is 15.8 versus less than 1 petaflop. The pattern is clear: the longer the context, the bigger the advantage grows. They also compared it against flash attention too, which is already one of the most important speed improvements in modern AI. Flash attention does not change the underlying math. Attention still scales quadratically, but it is extremely well optimized and used almost everywhere. SubQ is not beating something slow here. SSA reaches parity with flash attention 2 at around 16,000 tokens. But it runs 1.8 times faster at 32,000, 7 times faster at 128,000, and 56 times faster on a single attention layer at 1 million tokens. We are talking about 966 milliseconds versus over 54 seconds on an H100 GPU. These efficiency gains completely change how we can build and train these models. With dense attention, million token experiments are so expensive that most teams can only afford a handful of runs. With SSA, things changed. They ran more than 100 long context experiments across 6 major model generations. Normally, that kind of rapid iteration is just way too expensive at these context lengths. Now, they didn't actually train this model from scratch. What they did was take an existing open-weight frontier model, swap out its dense attention for SSA, and then stretch the context window in stages, going from 262,000 tokens, all the way up to 2 million. They used a technique called yarn to scale the position embeddings at each step. But it wasn't all smooth sailing. During training, they hit a really classic roadblock. As the model got better at retrieving information from deep inside the context, its actual reasoning and factual knowledge started to slip. This is where a lot of long context models quietly fail. They had to tune the model carefully to keep everything in balance: coding, instruction following, retrieval, and general knowledge. So, how does it actually perform? Let's look at the benchmarks. On GPQA Diamond, which is a brutal graduate-level science test, SubQ 1.1 small scored 85.4%. Now, to be fair, that is below the heavyweights. GPT 5.5 scores around 93%, and Claude Opus 4.8 is at 92%. But it did beat GPT 5.4 Nano and easily outperformed Claude Haiku 4.5. The key takeaway here isn't that this is the absolute smartest model on Earth. It's that the model kept its core reasoning intact while handling massive context lengths. On coding benchmarks like LiveCodeBench, it scored nearly 90%. That actually puts it slightly ahead of Claude Sonnet 4.6 and right on the heels of Opus 4.8. But the most interesting test is Automation Bench Finance. This one is designed to mimic real business tasks. The model has to navigate about 500 API endpoints across 47 different apps, figure out the right sequence of actions, ignore messy data, and get the exact right answer. There is no partial credit here. You either get it right, or you fail. On this test, SubQ 1.1 small scored 13%. That might sound low, but look at the competition. GPT 5.5 scored 18%, Opus 4.8 got 16%, and Claude Sonnet 4.6 only got 8%. Seeing a small, specialized model keep pace with the most powerful frontier models on a brutal, real-world task is, well, it's incredibly rare. And these aren't just self-reported numbers. Subquadratic had Appen independently verify them. Appen confirmed the exact matches on every single sample at 1 and 2 million tokens, and verified the 98% accuracy at 12 million. But let's be real for a second. We have heard big promises about long context before. It is easily one of the most overhyped areas in AI. The gap between what a model claims it can do on paper and what it actually does in production is usually massive. When Subquadratic first came out of stealth, the community was deeply split. Some people were thrilled, others were incredibly skeptical, calling it either the biggest thing since the Transformer, or the AI version of Theranos. The fact that they built on top of existing open-source weights instead of training from scratch made sense for their size, but it definitely added to the skepticism. And honestly, we've seen this movie before. Back in 2024, Magic.dev announced a 100 million token model with a claimed 1,000-fold efficiency advantage. They raised $500 million, but by 2026, there was still no real evidence of wide adoption. Other architectures like Mamba, RWKV, and various hybrids promised to break the quadratic bottleneck, too. But most of them ended up sacrificing quality, keeping expensive dense attention hidden somewhere in the system, or only delivering minor improvements. Subquadratic's first launch also had issues. Their benchmark suite was very narrow, focusing mostly on coding and retrieval, basically, the exact areas where their architecture was designed to win. Some tests were only run once because of high costs, and there was a noticeable gap between their internal results and what the third-party testers actually verified. The SubQ 1.1 small release is trying to fix those doubts with broader benchmarks and more third-party testing. But at the end of the day, benchmarks don't matter. What matters is what happens when real developers start throwing their messy, unoptimized data at this thing in production. Can this model actually hold together when reading a sprawling code base that was never formatted for a benchmark? Can it make sense of a poorly structured legal contract? Can it track details across 50 earnings reports without dropping the ball? Subquadratic is rolling this out to design partners right now, with a general release plan by the end of the year. They've backed this up with $29 million in seed funding, valued at $500 million, from investors who got in early on Anthropic, OpenAI, and Stripe. If their larger models can deliver on what this small model suggests, the impact on the industry is going to be massive. Think about it. Almost all of today's enterprise AI infrastructure exists solely to work around the limits of attention. The vector databases, the complex RAG pipelines, the chunking tools, they are all just scaffolding built to handle context scarcity. When a model can't hold a full contract or a full code base in memory, you have to build a pipeline to feed it fragments. But if you remove that bottleneck, the entire architecture changes. Sure, retrieval will still matter for massive databases or fast-changing data. But for a single, complex document or code base that fits in the window, the model can finally read the whole thing. No more guessing. No more missing critical connections. That is the real bet Subquadratic is making. They aren't just trying to build a faster attention layer. They are betting that the entire way we build enterprise AI today is designed around a bottleneck that doesn't even need to exist. If they are right, we might look back at the era of complex RAG pipelines and vector databases as a temporary workaround to a problem we finally solved. So, here is what I'm wondering: if you could suddenly feed an AI 12 million tokens of data cheaply and reliably, what is the first thing you would throw at it? Would you dump your entire company's documentation in, or is there a massive code base you've been waiting to analyze? Let me know in the comments below.